let's solve this problem number 2. Again, we are asked to find out the values of these support reactions and also the values of axial forces, shear forces, and bending moments at any section of these members. In other words, you are asked to analyze this frame using the stiffness method. Okay. So now let's solve this. We have only this one change. We have now a lateral load acting, a 5-kip load acting here, but it is acting exactly at the middle of this pane, which is 6 feet from the top, and 6 feet from the bottom. Okay. Now we have also changes in this in these spans of the members. Now we have this member spanning 20 feet, member BC, and member AB is spanning 12 feet. Also, we have a change in this load. This is now 1 kip per foot as compared to 2 kip per foot, which was acting in the previous sample. EI is constant again. Now, what is the value of kinematic indeterminacy? Again, this B will rotate, this C will rotate. So 2 degrees of kinematic indeterminacy if we neglect the axial effects. Okay, so now where will be our D1 and D2? So now you specify them. Here will be our D1. You can call this as your D1 also, but then you have to change all the things in the remaining steps. Okay, so I have chosen this to be D1 and this to be my D2. What are the values of D1, D2? This will be the initial aim of our analysis. So this is D1, this is D2. We have to find the values. What is our AD1 and AD2? Both are 0. Why? Because there is no external action acting corresponding to D1 and D2. Now, in the next step, I want to restrain my frame against the displacements. Okay, I'm going to restrain the frame against any kind of possible displacement. How can I do this? I fixed this end, this joint B, and also fix this joint C. This becomes now my restrained frame. Now, ADL matrix, where it is coming from now? ADL matrix is coming from when you apply your actual external load on your frame structure, and you find out the fixed end actions, and then you take out the values of the fixed end actions corresponding to D1 and D2, and you consider them as your ADL1 and ADL2 respectively. Okay, what is my ADL1 now? ADL1 is the value of the moment here. This fixed end moment, 7.5 kip fit, plus this kip fit value, this moment value, 33.3. Now, which will be clockwise? Which will be anti-clockwise? Now, this is clockwise. This is anti-clockwise. Anti-clockwise will be taken as negative. Clockwise will be taken as positive, which means that the ADL1 value will be this 7.5 minus 33.33. Why this is taken as negative? Because our assumed direction of D1 is clockwise. So if there is any fixed end moment which is anti-clockwise, we have to take that with negative sign. If you remember from the previous problem, there was no bending moment here. But in this case, we have a bending moment. Why? Because now this fixed end moment is coming from this load. By what? By which formula? By this PL over 8. Okay. And now we have also this horizontal reaction, which is okay. So it means that our ADL1 value is 7.5 plus 7.5 minus 3.3, so we get minus 25. Okay. What is our ADL2 value? Now, ADL2 value is this value, 33.3. Clockwise, so positive. This becomes our ADL matrix. Now, I quickly go through the stiffness coefficient matrix. Very simple. Again, you have to apply first a unit displacement at location number 1, and then find out these fixed induction values, these induced moments. Okay, what values I am going to pick from this slide is my S11 and S21. S11, 81 due to 1, so this 4EI over 20 plus this 4EI over 12. And S21 is this value. Okay, so now here you can see that this is now S11 value, S21 value. Now, in the next step, I'm going to apply the unit rotation at coordinate number 2, and these are the induced moments and reactions. So values I can get from this slide are S12 and S22. 81 due to 2, 82 due to 2. So 81 due to 2 is this value, 2EI over 12. And 82 due to 2 is this 4EI theta over L. Theta is equal to 1, so this becomes 4EI over 20. This value now. So now, if you put all these values in the form of a matrix, this becomes our stiffness coefficient matrix. And then you put all those matrices here in this equation. So this is our stiffness coefficient matrix. Okay. This is our AD matrix, AD1, AD2. This is our ADL1 and ADL2 value. This becomes my D matrix, D1 value and D2 value. Again, the negative sign is showing that the direction of your D2 needs to be reversed. So now I put these values of D1 and D2 here, this equation. And I need again to find out the AML matrix and AMD matrix for member AB. So to find out the member inductions. So I think you can now do it because it is repeated quite many times now. So this becomes AML matrix. These actions are coming from when you apply your external load on member and then find out the fixed inductions. Okay, now here we have a bit changed our normal notation here. Now, if you see here in the previous problem, we have assumed this upward to be our AM1. Now we have chosen this to be our AM1. Yes. Now, if this is my AM1, so my AML1 will also be corresponding to this AM1. This is just to tell you that if you change even their locations, so there will be no effect on the overall results. Okay, so if you take this is your AM1, this is your AM2 and AM3, AM4, AM5 and AM6. So corresponding to these locations, you will have your AML matrix values and AMD matrix values also. This is our AML matrix. AML1, AML2, AML3. Similarly, this is our AML1. Should be negative. Why? Because opposite to our estimation of our AML1. AML2 is upward. This is upward, so positive 10. AML3 now it is clockwise. But here it is anti-clockwise, so this will be negative. Similarly, AML4, AML5, and AML6 values. Okay. Similarly, now you can obtain your AMD matrix. First, unit rotation at coordinate 1 and find out the values of your AMD1, 2-1, 3-1, 4-1, 5-1, and 6-1, which are this AMD 1-1 is this one, AMD 2-1 is this one, and AMD 3-1 is this one. Similarly, AMD 4-1 is this one, AMD 5-1 will be this reaction here. AMD 6-1 will be this moment. Similarly, now you apply this unit rotation at coordinate number 2, and you find out these values of AMD 1-2, which is 0, AMD 2-2, AMD 3-2, which is 0, AMD 4-2, which is 0, AMD 5-2, which will have the same value as this one, but opposite in sign. And AMD 6-2 will be 0 also. You can see this, they have opposite sign. And now you put these matrices here and you obtain your member interactions for member A. Similarly, you solve now the next member after drawing the shear force and bending moment diagram for this member AB. This is the member BC. Okay. You first choose your direction and location of AM values, and then you calculate your AML values and AMD values, and then you find out the member interactions by solving these matrices. Then you draw the shear force and bending moment diagram. Now let's solve this problem. This is the problem number 3. And we are asked to analyze this frame using the stiffness method. Now, this joint B, at this joint B, now we have 3 members connected. Member BC, member BE, and member BA. Similarly, at this point or at this joint E, we have these 3 members connected. Member EB, member ED, and member EF. So now if you want to find out the degree of kinematic indeterminacy, so you know that when load will act on this member BE, it will cause these 2 joints, B and joint E, to rotate. So we will have one rotation at this joint B, and we have one other rotation at this joint E. So now these will be our 2 unknown displacements. EI is to be constant for this whole structure. So now let's do this. Our first displacement, we have specified it as D1. This is our D1. And we have specified our D2 here. D2 now. What are the values of D1, D2? We don't know these values. We don't know that how much this joint B will rotate, how much this joint E will rotate. If we find out these values of rotations, we then will be able to solve the whole structure. So D1 and D2, they are the unknowns. What is the value of AD1, AD2? Again 0, because we don't have any external action at D1 and at D2, or corresponding to D1 and D2. Okay. So now let's solve this. The step number 2, we apply the external load, which is 2 kip per foot. And under this load, we find out the fixed end action. So the fixed end moment value here, 96 kip feet. Here, 96 kip feet. Similarly, we have these reactions. So now, and we don't have any external load acting on this member, also no load acting on this member, and also no load is acting on these two members. Okay, so now our ADL1 value will correspond to location number 1, and location number 1 is shared between 3 members, with this member, and this member. We need to take the values of the moments from all these 3 members at this point. So if you look at our first member, we have a 96 kip fit moment anti-clockwise. Anti-clockwise should be taken as negative. So this is minus 96. Then we look at this member. Do we have any moment? No, 0. Do we have any moment in this member? No, 0. So it means that the ADL1 value will be minus 96 kip feet, which is written here. Then we go to the next coordinate, and we see that this coordinate is also shared between the 3 members, member BE, member EF, and member ED. And if we look at the moment, so we have this moment 96 kip fit clockwise, so positive. Do we have any moment here? No, 0. Do we have any moment at this point? This member, EF? No, we don't have any. It means it will also be 0. So the ADL2 value will be 96 kip feet. Positive. Why? Because it is clockwise. And our assumed direction of this G2 is also clockwise. This is the ADL matrix. Now we come to the step number 3, where we have to find out the values of the stiffness coefficients. So first we do apply this unit rotation at coordinate 1. Now you know that coordinate 1 is shared between 3 members. It means that if you rotate this point B, it will induce moments in all these 3 members. And what will be their values? Their values will be at the near end 40i over 40i theta over L, and at the far end 2i theta over L. Okay. So these are the values at the near end, and at the near end. At the far end, we have these. Now, okay, we know this. Now, what we need to do now, we need to find out the coefficients. So, what coefficient I'm going to get from here? This S11 and S21. 8-1 due to 1, 8-2 due to 1. So 8-1 due to 1 means now we are going to take all these 3 moments. This 40i over 12, this 40i over 24, and this 40i over 12. We have to sum them because all of them are clockwise. So here we go. 40i over 12 plus 40i over 12 plus 40i over 24. So when they are added, we get this value of our S11 coefficient. Similarly, S21 is at this end, corresponding to coordinate number 2. We have this 2ei over 24. We don't have any moments induced in these members, member ED and member EF, so they will be 0. So the only value we have is 2ei over 24 as our S21 coefficient. Now, we apply a unit rotation at location number 2. Okay. When you apply a unit rotation at joint E, it will induce moments in all these 3 members because they are connected at this E. And what will be their values? Now, these are the values of these moments. 40i over L at the near end, 40i theta over L at the near end, and 2i theta over the far end. Similarly, these are the compensating reactions. Now, what values I'm getting from this slide? S12, 8.1 due to 2 and 8.2 due to 2. So 8.1 due to 2 is this value S12, which is 2i over 24. Why it is 2i over 24? Because it is at the far end. And there is no moment induced in this member. Also, there is no moment induced in this member because we have fixed this joint. Okay. So now we pick these values. And what will be the value of S22? S22 will be the sum of these three moments. This 4i over 24, this 4i over 12, and this 4i over 12. Now let's see them. Here we go. We have these values. This is 2i over 24 as our S12 coefficient. And S22 coefficient is the sum of these three values of bending moments. 4i over 24, 4i over 12, and 4i over 12. So we get these values now. So now if we put them in matrix, so we get this matrix as our stiffness coefficient matrix. Now we need to solve this equation. Okay, so this is our stiffness coefficient matrix. AD values, AD1, AD2, ADL1, ADL1, ADL2. If you solve them, these are the values of D1, D2. Now you know why there is negative sign, because of the resume direction of D2 needs to be reversed here. Now we solve the member end actions. So when you solve the member end actions, as we did quite many times, you will get these values of your member end actions, and then you can draw your shear force and bending moment diagram, which will be your home exercise. Okay. Now let's solve this structure also. If you have any question at any point, now you can ask at any point. Problem number 4. And remember, this is non-straight frames. Okay. So now we have this load acting here. 60 kg, 3 kg per foot load is acting. And it means that the length of this member is 15 feet. The length of this member is 20 feet. And this member is having a length of 10 feet. 3 kg per foot uniformly distributed load is acting on this member BC. And a point load 60 kg is acting at this member AP. EI is constant for this problem. What will be the degree of indeterminacy? Now we know that. Again, we will have rotation at this point B, rotation at point C. D1, D2, we have to find these values. AD1, AD2, both are 0. Then you restrain your structure against these displacements. Now in the next step, you find out the fixed end actions due to the actual applied load. Okay. And you find your ADL1 value, ADL2 values. And then you give a unit rotation at B. It will induce moments in all these members which are connected at this point. And you find out your S11, which is this this moment plus this moment plus this moment. S21 is this value. Similarly, now you apply a unit value of rotation at this coordinate number 2. This rotation, you find out these moments, these reactions. Now S12 will be this one. No value coming from this member, no value coming from this member, because both are 0. And the value of S22 is 0.2 pi. This becomes my stiffness coefficient matrix. You can put all these values now here in this equation, and this is the stiffness coefficient matrix, AD1, AD2, ADL1, ADL2. You get these values of G1 and G2. Again, negative sign, so the direction of G2 needs to be reversed. Using this G1 and G2, you can find out the member inductions, and this will also be your class exercise. You remember, if you don't draw the shear force and bending moment diagram, so it means that your analysis is incomplete. You must draw the shear force and bending moment diagram, even if they are not asked. Okay. So now you know very well how to draw them. So this will be class exercise. is no this axial force here. And similarly, you can get your AML2